So, in the last lecture we came across the plastic zone correction which was proposed by Irwin, and we also learned the iterative method of finding out the fracture toughness. We have established this fact that the critical value of a stress intensity factor in mode 1 is K1C, which is the plane strain fracture toughness of the material. So, this is the parameter. It is similar to how in stress strain curve the stress increases and it reaches a value where we want to define the yield strength, then there is a value where we want to define the ultimate tensile strength. Similarly, as we increase the stress on a specimen which has a crack already, and we keep on pulling it and we apply a value of a stress which will be increasing gradually, then we will be increasing the K value, which will be some constant into sigma root pi a. So, as we increase sigma, the stress intensity factor will be increasing, and then we will reach a value which will be a critical value, after which this crack will start propagating, will increase in size. So, crack growth will happen, and that will be the fracture toughness value. So how do we measure it? That is one question we will be addressing, but before that we need to understand something, that what this alpha is. Alpha is a factor which differentiates if you have two different specimen geometry or if you have two different crack geometry. So, these are two different things. One we will consider. So, for example, if we have a crack which is at the edge of the specimen, and this specimen is being opened up in tension. So, the stress is applied there. Usually the stress is applied along this point, and this line is called a line which passes through the loading point and the crack tip is called the load line in the language of testing. So, this configuration is different from this configuration of crack, where the crack is inside the material. Okay. So, this in this case also you apply stress and you fix the lower end, but and given the same material, if you apply the stress, then you will get different amount of stress intensity factor even if the crack lengths are same. That will be because of the constraint, and this constraint is a little different from what we addressed before. So, you see, if you divide it hypothetically, then this part, the left part, is the mirror image of right part. So, the right part is equivalent to this one, but is it? Do you have any difference between this condition and that condition? So, if you take half of it, is that exactly equal to this or not? The answer is that the right part of this is not equal to that, because in this case on this surface you do not have any constraint. So, this surface is free, but in this case this hypothetical, along this hypothetical line you have a constraint, and that constraint is the symmetry constraint. So, if this is my x axis, this is my y axis. So, along this line you have symmetry on x axis. So, you have x symmetry. Okay. So, this is the axis of symmetry, and you have to maintain same. So, imagine a point here, and this point cannot deform freely as it will happen in this case. So, in this case it has to have a continuum with the left hand side, right. So, that will cause a constraint on this type of geometry, and therefore, these two ends will not open up as easily as in this case. So, in this case this end will open up very easily in comparison to this one, and that is why you will have different value of k which can be given by the factor alpha, which is the shape factor in this case, and that shape factor is arising because of the difference in the geometry. So, the stress intensity factor in this case will be 12% higher than what you will obtain in that case. Okay. So, in that case alpha, in this case for edge crack, this is called edge crack, this is called embedded crack or central crack. So, in case of edge crack, it will be 1.12 into sigma root over pi a, and this 1.12 is 12% higher than what you will have when this value will be 1, when alpha will be 1. Okay. So, the fracture toughness of this edge crack will also be higher because it is tougher. Why? Because it can open up more than this one, it has less constraint in comparison to that one. There are different standard geometry which is used. So, for example, in tensile testing we learnt that we cannot just take anything and test it, we have to have a defined specimen dimension and geometry. So, usually at the end we have threads in a tensile specimen which is fixed with the machine, then you have a fillet radius, and then you have a parallel length which is called the gauge length, and after that you again have the same thing. So, this was our tensile specimen. So, the gauge length versus the diameter has to maintain certain ratio which is given in the ASTM standard E8, which has been shared with you in the Google Classroom. So, there are some geometries which are approved by the ASTM standard. There are different standards which are followed throughout the world when we talk about testing of the material. So, ASTM is one type of a standard which is American standard of testing materials. Then you have European standard. So, that is that are coded by ESIS, and then there is a certain code number. So, this is European Structural Integrity Society. Then we have Indian standard also, which is IS, Indian standard, and apart from that we have British standard also, and British standard is usually a little different from American standard. I am not so sure if there is any Russian standard, but there should be. So, there are different standards. So, and usually mostly in our country we follow ASTM standard as long as the mechanical behavior and testing of materials is concerned. So, for tensile specimen we have round cylindrical specimen which is standard, then we have rectangular specimen where you have this kind of rectangular piece, and so this is how it will look like in 3 dimension. Okay. So, this will be a rectangular bar where you make this kind of geometry, and then you fix the end by pin or by friction. So, you plug it in the grips. So, round and rectangular specimens are standard specimen. Similarly, in fracture toughness testing we have certain geometry, and we already have understood that because of change in the crack geometry or specimen geometry, we will have difference in the fracture toughness measurement, and therefore, it should be remembered that if we use different types of a specimen, then we need different formula for calculating fracture toughness. So, this alpha will be changing. This stress intensity factor is also a function of A. Okay. So, A is the crack length, but more than that, the geometry of crack also depends upon how deep is the crack. in the specimen. So, let me explain that part a little in little detail. So, for instance, this is my specimen where this is 10 mm and the crack is 5 mm deep. Okay. So, you can have another specimen where this is 12 mm and this is 6 mm, but those two specimens will be same as long as crack geometry is concerned. Although crack length is different, in that case the crack length is 6 mm. In this case, so let me make that part also. So, in this case this distance is 12 mm and the crack length is 6 mm. Okay. So, A has changed, okay, but stress intensity more than the absolute value of crack length, it is dependent on a geometrical factor which is the ratio of the total width of the specimen and how deep is the crack. Okay. So, in this case it is 5 by 10 which is 0.5, in this case also it is 0.5. Okay. So, if this crack grows deeper or if you start initially with a deeper crack, but do not change this dimension, then you will have comparatively deeper crack. So, instead of 0.5 it will be some different ratio. So, if it is 6 mm in 10, then that will be 6 by 10. So, 0.6 will be the ratio of the crack depth in comparison to the width, and this k is a function of that value also. Okay. It is a function of, so it changes how deep the crack is, it depends on that also. So, there are many factors which we must take into consideration before judging that if this material or is tougher or this material is tougher. Even if two materials are same, if this specimen is showing more fracture toughness or if this specimen is showing more fracture toughness, we have to calculate fracture toughness in order to know. So, fracture toughness will not have any problem because it is designed in such a way, the formulation is in such a way that you calculate a value which you can compare with two different geometries, and that is how a material property should be defined, that once I tell you that this is the yield strength of this material, I should be able to compare it with the same material of different dimension also. If not, then the differences must also be reported or defined very clearly, and that is how a material property definition works. So, let me go to the next page and then we will discuss more about the effects of crack geometry and different types of specimens which are the standard specimen. So, according to American standard, we have one specimen which I usually draw, which looks like this, and if I have to make it very specific, so this is how the specimen looks like, and usually when I draw this in 2 dimension, I fix the lower part and I pull the upper part, but it is not like that. Usually the specimens have holes and these holes are through, and you put a pin similar to what we do in the rectangular tensile specimen. You put a pin inside and that pin is held by the machine on both sides. The lower part does not move, the upper part moves. So, these are holes, okay, and the center of these holes usually are in alignment with the crack tip. So, I have drawn here is not correct. So, the hole should have been here and the center of that hole passes through the tip of the crack, initial crack, okay, and then you pull the upper part, fix the lower part, and you keep on pulling until there is a crack growth. This kind of a specimen is called compact tension specimen. Compact tension specimen, the short form is CT specimen. The other type of a specimen which is used in testing is, another question is that why do we have different shapes of specimen? So, why do we do tensile testing in a cylindrical bar or in a rectangular bar? Why can't we do it on only cylindrical bar? So, this is another type of a specimen where this crack is also through and through, but in this case we do not have holes, and in this case lower part, there is no lower part. So, these are sides. So, we test it in 3-point bending. So, we have a roller here, we have a roller there, which will be like this. So, these are rollers, and then you have another roller here, okay, and these two are fixed, and this one you are pushing down, okay. So, this is called 3-point bending, 3 points bending because you are bending it, okay. So, if you want to imagine how the crack will be, then initially my specimen looks like this, right, and then I push it. So, I apply force. So, in this case I was pulling it, in this case I am pushing it. So, I apply force, and then after some time the specimen will look like. So, let me draw how it will look after some time. So, it will look like this. Okay. So, because you have applied this force here, it will bend and the rollers will be here. So, it will bend and crack will grow if you have crossed the K1C. So, fracture toughness value, then the crack will grow from the initial value, and this is how the specimen will be tested. So, this is 3-point bending. You can have sometimes, very rarely you can have 4-point bending, because in bending you have, in this case you have shear forces also. So, it is not complete bending, so not pure bending, but when you apply 4-point bending, then you avoid those shear stresses. So, you have pure bending situation in that case, but even then 3-point bending is more general. So, this is called single edge notched bend specimen. Sometimes it is also called 3-point bend specimen, but 3-point bend specimen name is not suitable, because it tells you that the specimen is being bent in 3-point, but it does not tell you that if you have a crack or not. So, you can have 3-point bending for just a rectangular bar which have no crack in it, and that's also a common test. So, you have rollers here and rollers here and here, and you bend it similar to that, but you do not have a crack. So, in this case what you get, the property which you get is flexural strength, a bending strength, okay. But if you have a crack, so in fracture toughness you will have a crack which is on one side, right. So, it is not embedded. In this case also it is not embedded, in this case it is not embedded. So, this kind of crack is called edge crack, but you see that we do not write it crack, we call it edge notched, okay. So, we will come back to this part, but before that let me tell you this different type of standard specimen. So, we have single edge notched bend specimen, and the short form is SENB. A specimen, this is TPB, it is called 3-point bend specimen. When we talk about fracture toughness, if it is clear to you that it is about fracture toughness, then 3-point bend specimen or TPB would mean this specimen, but if it is not sure, then it might mean this one also. So, this is more preferred, SENB is more preferred. Apart from this, in old days, so fracture toughness is not very old, it started, you know that it started with Irwin probably, so 1940 or later than that. So, it is not very old, but even then it is comparatively old. So much before, because we started with Griffith and English, and they calculated on a through crack which was in the center of the plate. So, this kind of a specimen was also used, which is called central cracked panel. However, the short form or middle cracked, so the short form was MT specimen, middle cracked tension specimen. So, it is loaded in tension like a tensile specimen, but this is not used anymore. Apart from that, you have similar to this, you have another specimen which looks like this. So, you can have hole or you can fix the upper part and you can pull it in tension. So, you can fix the lower part. So, this has, instead of having single notch, you have double notch. So, this specimen is called double edge notched tension specimen, DENT specimen. Apart from that, there is one more specimen which is given in the standard, which has similar to this. So, very similar to this. It is actually exactly this, except that it is in the spherical or disc shaped. So, it looks like this. So, you have hole here, you have hole here, and it looks like this in 3 dimension. So, this is called disc compact tension specimen, DCT specimen. So, CT, just add a D there and this will be the shape, and then it will be called DCT. So, why do we use such different types of specimens? Why can't we just be happy with one type of specimen? The reason is that the type of material we develop in the, and why do we, so the first hand testing happens in the research, and after that, once the research is done, then it becomes commercial, and once it is commercial, materials are produced in industry and they are sent for making different components. So, these materials, when they are sent in different industries for making components, they are tested for the quality assurance. So, you want to know that this grade of steel has been made or this grade of titanium alloy has been made, and these are the property, these are the yield strength, fracture toughness, and all those properties are tested. But there can be different reasons, but one of the reason is that when the material is being developed in the research level, so then you do not make in bulk, you do not make the material in bulk, you make the material in very small quantity because it is just for research purpose, and therefore, you cannot have a lot of material available with you. So, for example, you made only 10 by 10 mm small piece. So, this is 10, this is 10 mm. So, this is a very small piece of material which you have made in lab, okay? And now you want to know different properties of this. So, apart from being the size, there can be different constraint that in which form you are making the material. So, if you are making the material in rectangular form, then this kind of a specimen can be cut from this, right. So, you can cut this kind of specimen, make holes in it and do the testing. But if you are making something in the cylindrical form, so if you are drawing a wire, you are making a wire in the lab. So, can you do this kind of testing? Is it possible to make this kind of specimen out of this? This kind of a specimen making out of this is not possible, because if you are making wire, then this dimension will be very small, okay. So, making this kind of a specimen out of it will be, first of all, you will be losing a lot of material, because you will be cutting a lot of material and you will have to throw those things out. Apart from that, you may not be able to make this kind of material because you have certain limitations to have certain ratio maintained. So, this must have some dimension in comparison to the hole you are drilling. Okay. So, it may not be possible for you to make such specimen. Then what you do is you cut a disc like a coin. Okay. You cut disc and make this kind of specimen. Okay. If you have very small amount of this specimen, then it is easier to cut only rectangular blocks and make this kind of specimen, because then you will not be losing a lot of material, because you have developed this out of research and you do not want to waste material in cutting process. So, you cut rectangular pieces and make this kind of material, and this kind of specimen will result in less loss of the material in comparison to this kind of specimen. Okay. So, these are the reasons why you want to have possibility to test different types or shapes of a specimen and still get the same parameter which you can compare. So, if you obtained fracture toughness from this test, that should be comparable with this one. Okay. So, it should not be that the fracture toughness obtained from this kind of a specimen should be different if you measure the fracture toughness from this kind of specimen. It should be same, because it is a material property. So, you have to take care of the geometry factor, and that is why you have that alpha factor there. You do not want to forget about it, you want to remember, you want to put it in the formulation, so that whether you test this specimen or that specimen, you get exactly same value for the same material. Okay. So, of course, we are not talking about the effect of thickness. So, if we test this specimen or that specimen, we must make sure that it is in plane strain condition as long as K1C is concerned. K1C has to be tested in plane strain condition. Okay. So, this is all. Then we will talk about another limitations, and we will talk about the standard procedure of fracture toughness testing in plane strain in our next lecture. Thank you.